So last but not least in a long string of videos that I'm making tonight, we have assignment number 3. So for those of you who are out, wanted to review, whatever it might have been, here's your walkthrough. Naturally, this is what we did in class. I'm going to do the couple of them here, and then I think this one is due for homework. Literally the 2 problems that follow are due on, Thursday at midnight, I believe. Anyways, so we've got a cart. You're pulling this wagon, you're pulling this cart with a mass of 40 kilograms, and they want to know what the horizontal acceleration of this cart is going to be. Now, any acceleration horizontally in that x-axis is going to be the result of a force exclusively in that x-axis. What you should recognize, or maybe briefly remember from our last unit, is that forces at angles can be resolved, right? And so I can take this force of 80 newtons at 20 degrees, and I can find out what my vertical force is, and I can find out what my horizontal force is for each one of these. And if I wanted to draw the entire free body diagram, you would notice that there is a horizontal component to this force. There is a vertical component to this force. Why doesn't the wagon move upwards at all? It's probably because there's also a weight force working on this wagon, keeping it pinned to the ground naturally. And so the one force, if we want to look at it from a net force perspective, the one force that isn't potentially canceled out is going to be your horizontal force. So that horizontal component to the 80 newtons, the horizontal piece of that vector at that angle, is going to be what's responsible for this horizontal acceleration, moving left and right along the x-axis. Notice that this equation, again on your the front of your sheet, on the front of your unit packet, is the exact same as the velocity equation was from our projectiles and angles. That part hasn't changed. The trig is still the same. And so if we want to find the horizontal component to this force, it's going to be our 80 Newton force that we start with, that we're working with, multiplied by the cosine of our angle, which was 20 degrees. Multiply those two, make sure you're in degrees, not radians, and you should get a horizontal force of 75.2 newtons. Now that is just the horizontal left-right component to this, but it is what we're going to take over to F equals ma, because remember, this is your net force, and your vertical component to this force and gravity have canceled each other out. It's not moving up or down, and so the only thing left over, the only thing that's causing this wagon to accelerate is your horizontal velocity, your horizontal force, which causes it to accelerate and gives you that horizontal velocity. But it's going to be 75.2 newtons is equal to 40 kilograms, because that was the mass provided at the beginning, multiplied by your acceleration. You should get a value of acceleration of 1.88 meters per second squared. There you go. That's how quickly that particular wagon will accelerate horizontally left and right. Yes, I'm ignoring friction for now. We won't forever, and this will get one little piece a little bit more complicated, but that's about all. I am going to ask quite a few questions like number 2 on the exam, because once you see the shortcut here in a second, you'll realize just how fast it is. If I want to increase the mass of the wagon from the previous problem by a factor of 3, I am going to look at the value I had for mass in the previous problem. It was 40 kilograms, and I'm going to triple it, right? Multiply it by 3, and that's going to be your new force. So the math works out to be the exact same all the way up until this point. 75.2 newtons is equal to not 40, but 120 kilograms, because that is 3 times larger, multiplied by my acceleration. You could do the whole math problem again, and you'll get an acceleration of 0.63 meters per second squared, and that is perfectly fine. That's a great way to do it. I think it takes some time, because you've got to think about what your force was and all of that stuff, and I'm going to show you a shortcut. If you type this into your calculator, right, our acceleration from this problem and our acceleration from the last problem, and you type this into your calculator, you're going to get a fraction of, not 1 second, sorry, 1/3. This is going to simplify to be, well, it might come out as a decimal at 0.03, but 0.33 is the exact same as 1/3. And that's the way this will always work out. And this comes back to our inversely proportional talk that we had, well, first and foremost, way back in Unit 1, but in Assignment 1. So if you missed that inversely proportional, directly proportional stuff, Assignment 2, then go check out Assignment number 2. And because it was inversely proportional, if you triple your mass, you're going to get 1/3 of your acceleration. This is always going to be true. If you doubled your mass, you'd get half the acceleration. That's a question on assignment number 2, I believe. If you had quadrupled your mass, you'd get 1/4 of the acceleration. If you cut your mass in half, you'd get twice the acceleration. They're always inversely proportional to one another, and that's always going to be the case. You literally could have just wrote something like this on your exam, if you wanted to do this on the exam, and then just divide 1.88 by 3. That's good enough for me. That's showing your work. But you've got to show this part right here. I'll highlight it. You've got to show that part right there. Otherwise, I don't know where your head's at. I don't know why you're dividing by 3. It'll look like an arbitrary random number. So tell me why you're doing it, and we're good to go. Last but not least, this is the last one I went over. I wanted them to do 4 and 5. You can cross out 6 and 7. I took those off the exam because they were a shortened year. We're just not going to have time to do justice to those problems, I guess I could say. So John slaps the side of a building. On which object is the force greatest? John's hand or the building? So there's a building. Someone comes in and gives it a really, really, really good slap, right? This is where your hand is. I'm going to label it with the letter H because I'm not about to draw a hand on paper, let alone a stylus. So the hand comes in and it slaps the wall. You're applying a force to the wall. Yes. Newton's third law, and this is a conceptual question, obviously, but Newton's third law states, and I'll spark note this in a second, Newton's third law states that for every action there's an equal and opposite reaction. What that actually means is that forces come in pairs. There's always 2, right? So my hand hitting the wall would be one force, but the wall is made up of stuff, right? It has material, it has atoms, and I mean, they're not cells, obviously, that's in my hand, but, you know, blocks that it's made up of. It's, you know, got these little tiny compound molecules that form these lattice structures inside, whatever. The idea is that it's solid, and you're not going to be able to move through it very easily. You could, with enough force, break all of the chemical bonds and everything holding that wall together. That is possible to do. Obviously, people have punched holes in drywall before, or golf balls have come through windows, or you've seen a wrecking ball take down a concrete wall when Mr. Willis's hand slapping that wall in class didn't do anything, right? So these forces always come in pairs. And as your hand, in this problem, applies a force to the wall isn't going to let you occupy the same space that it already has, and it will apply a force back to you. Right? That force is directly proportional to how strong the intermolecular forces from chemistry are that hold that object together, which is why if you punch a cinder block wall, your hand breaks, the wall doesn't. But it's the fact that it is held together by those chemical bonds, and it's those chemical bonds basically not allowing your hand in, not allowing your hand to occupy that same space. Your electrons are being repelled by the wall's electrons, sort of thing. And so the wall applies a force back to you. Generally, these are equal and opposite. Not always, right? If you're a wrecking ball swinging through a cinder block wall, you'll be able to apply more force than the wall can back at you, and you'll crumble, and you have a net force going off in that direction. Or it could be a golf ball through a window, whatever it might be. But that is Newton's third law in a nutshell, right? It comes back to a little bit of chemistry. He predated the chemistry behind that idea by like 300 years. But the idea is that those atoms, those molecules, those chemicals that hold all of this stuff together in the entire universe don't want to occupy the same space at the same time if they don't have to. And so if you push on the wall, it's going to push back. Basically, I don't know, maintaining its territory, whatever. It wants to stay the way that it was. So that was about it. That's Newton's third law, and that was all I did for the homework for these guys. So for, what was it, Thursday at midnight, number 4 and number 5 are both going to be due. Really, that was all. So I hope that helped. Let me know if it did or did not.